Hello. I owe an apology to Ajit because of the scheduling. I also have an explanation. Well, when we have theme for every session, there are some outliers, and whenever there are outliers, there are reasons for that. One of the reason is Ayuka's Scientific Advisory Committee meeting is scheduled on 6, and many of my speakers also have to finish before that. So there is some mismatch which happened. He is the responsible person. Thank you. So we will have lunch in this guest house right now, and 2:30 to 3:30 there is a public talk by Shrinivas Kulkarni, followed by 4 o'clock there is a short session of book release by relatives of Chandrasekhar here, and then 4:15 to 5:15 we will have another public talk by Jayant. Thank you. Dear friends, we'll start the afternoon session. Somehow I have become, and also probably none of you noticed, my friend pointed out, I've become so informal that formalities are not kept. I should have first of all wished all of you Happy New Year, which I forgot. There's one more thing which I'll keep it for the next public talk. Before the public talk, I'll announce. I should have been a little more careful. I didn't do that, but I will keep it as a secret till for 1 more hour. But now we will have the part of the program we wanted to encourage the students to be benefited, and that is one of the reasons we have organized several public lectures as part of the Chandra centenary celebrations. And the first public talk is Shrinivas Kulkarni, who is from Caltech. He will talk to us, and the title is here. But it's my pleasure to introduce the speaker, Shrinivas Kulkarni, the MacArthur Professor of Astronomy and Professor of Planetary Sciences at Caltech. He is also Director of Caltech Optical Observatories. He is also Director of NASA Exoplanet Science Institute. He has also awarded A.D. White Professor at Large at Cornell. And he did his undergraduate. This is where our Indian connections come up. IIT Delhi. And he did PhD from UC Berkeley. And his primary interests are the study of compact objects. And he is keenly interested in developing or refining astronomical methodologies. He has won several prizes. If I start listing them, then our talks will be postponed by at least 1 hour. So I will suggest all of you to go to his web page and see, and at least it should serve as inspiration for many of the students that one should do extraordinary work like that. Now, Shrinivas Kulkarni will talk to us about astronomy on the cusp. He is also giving another talk as part of the conference talk tomorrow in the morning, and he was very kind. In fact, he was originally planning to come for only 1 day. I made a request. It would be nice if he stays for 2 days so that he can talk to our students and also all the faculty who are around here, and also take part, if possible, in the conference dinner tomorrow. He was kind enough to accept that, and he will talk to us astronomy on the cusp, driven by technology, today as a public lecture. Thank you. Please.
Okay, a very generous introduction. So I think today's talk is, I think, the odd man out, odd talk in a conference driven by symmetries and beauty. I will not talk of either of those two things. But for most of the young students, I think what I talk should be of more interest than many other talks. Okay. That's because astronomy is primarily driven by observations. Ideas are actually quite cheap in astronomy. And in astronomy, in my opinion, It's like exploring. You can sit down and think of many, many things, continents, other planets, but the whole business lies in making the measurements, because without the measurements, it's just ideas. And as I told you, ideas, in my opinion, are rather cheap. Okay, so with that completely anti-conference spirit introduction, let me go on to another statement, which is that, measurements is important, and measurements are so important that what really drives measurements is the ability to make measurements. So my thesis today is that much of astronomy progress is really driven by technology, because it's quite easy. You give me a topic, any topic, it doesn't matter. I've been around in this subject for a very long time, so I'm quite experienced. So you say, if you had a telescope which was square kilometer at optical wavelengths, I think 5 minutes later I can write to you, because I've been around a long time, all the wonderful things we could do. But it's a useless exercise, because you should first tell me how to build a telescope of square kilometer in size. And again, so those sorts of ideas are also very cheap. And astronomers do that very frequently. It's called white papers. So we're going to skip that too. So let's get to the heart of this business, which is the technology that you need to make or to exploit, and then everything else follows easily. So to summarize, theoretical ideas are cheap, white papers are even cheaper. The hardest part is figuring out what you can do today in the foreseeable future, which, at least in my horizon, is a few years. Okay? And so we'll go from there. So here's my summary of what I see astronomy. So between 1930 to 70s, stars were understood. We understand pretty much how stars work. Over that period of 50 to 80, we understood how the elemental buildup took place in the universe, how the universe, which began with hydrogen, helium, and sometimes I say, thank God, because of some of my colleagues, God even made some lithium. Okay. I guess lithium treatment is not so common here. Okay, anyway, so we had hydrogen, helium, and then the elemental buildup took place. Neutron stars, black holes, the ideas were around, but as I said, ideas, they're fine. But we actually have measurements which showed that these exist. We even have some ideas about basic verification of expectations of black holes. I would say in the last 20 years, to me, the most astonishing thing is as cosmology is understood, by which I mean two things. One is cosmography, which is what is the geometry of the universe. The other is how did matter get put together, sort of the growth of structure. Okay, so that's a pretty impressive achievement in astronomy. And you'll see, of course, when I made the statement, ideas are cheap, I mean most ideas are cheap. There are always exceptional ideas that do come along once in a while, and they're really exceptionally great. So I don't want to give the false impression that all ideas are cheap, but most ideas you come across are cheap. No, I'm not much into hero worship. Okay. So let's go through what I consider as the most amazing thing is this is how the universe, to me this is amazing because I don't work in this particular subfield. And what it shows here, and I'll play this movie again, redshift is the redshift counter is going on. And this shows how the universe began with almost a small amount of perturbations. You have energy, you have dark matter, ordinary matter, and gravity, and that's all that goes into this sort of simulation. And it's amazing that, to me, that you actually understand the growth of structure in the universe. So let me play this at a somewhat higher resolution. So the universe begins with an incredible almost smoothness in any parameter, energy, matter. It's so smooth that it took many, many years. It took 3 decades to actually see the small fluctuations in the original density distribution. Okay, even though the background radiation was discovered in 67, the first real evidence that you could actually see these fluctuations took about 3 decades. Okay, so I know many times it's very popular to say beauty is great, symmetry is great, but let me tell you one thing. If the universe was perfectly symmetrical and perfectly homogeneous, especially with no changes in its density, the universe would have been very boring. There would be no structure at all. So, in fact, most interesting things in life have nothing to do, in fact, have to do with asymmetries and small deviations from symmetries. Okay, so here's a slightly higher resolution, and this shows how this growth takes place. And to me, it's astonishing that this sort of picture, which only is 20 years old, is now verified with observations. It's not obvious at all that we would be able to, in some sense, play back the movie of the universe so well with such precision. Okay, and so this is my view of what I consider as growth areas. Okay, so and this is meant only for young people, because the older people, they'll still always be, of course, working on quantizing gravity or working on even more spherical black holes or things of that sort. So, but you guys who are young, you should go and make some real discoveries. And at least I thought a lot about where this growth is. And my idea of doing anything in science is you should always go where there's huge growth. It's much better to be lucky than to be smart. Much, much better to be lucky. Okay? So you want to work on old problems, you have to be very smart. And that's okay, except usually you're not. I'm giving you a statistical statement. Okay? But lucky, you can be with some thought. And that's, so here's my list. And within that, I'll give you a subset of what I want to talk today. Okay? And we'll return back to this list in a minute. Okay, so I'll return back to my thesis that ultimately the mother of all, I think, ideas that drive astronomy is technology. It's not the ability to figure out new things, what telescopes can do. It is whether I can build this telescope, build this gizmo. So the particular areas I want to focus are to do with exponential growth the most famous, there's a very famous empirical law. It's called Moore's law. Gordon Moore, the founder of Intel, he noticed back in the 60s that the transistor technology was doubling about every 18 to 24 months. So, and you know that's true because you can buy a digital camera this year and it'll have a certain number of megapixels. And in 2 years you can buy, for the same amount of money, you'll have at least twice as many pixels. So that is Moore's law at work for you. A less well-known law is Kurzweil's. He calls it a law, sometimes called Kurzweil's law of accelerating returns, which says that basically as technologies mature, the exponential timescale decreases. I'm not sure I actually agree with this. I have another explanation for that. So let's get the data, because laws and statements are all fine, but in the end you have to have data. And this is the original observation from Moore from his paper, which shows in fact the number of transistors in an integrated circuit as a function of time from 71, and it's been updated recently. And so this is you have a log on one axis, this is a log scale, linear on the other axis. It's a straight line. We all know, we all learned in 7th grade that a straight line in a plot of which log x, log y versus t means it's an exponential. Okay, so Kurzweil would say that if you actually put all this together, starting with vacuum tubes down to integrated chips, then in fact this is the exponential time is decreased. Which of course, it doesn't take too much mathematics to understand that if the exponential time itself is decreasing in the exponential, you'll soon hit into a singularity. And Kurzweil has many ideas about what that could be. And we're not talking about black hole singularities here, but something close. Okay, so let's look at Moore's law in astronomy. Here's an aerial view of the Palomar Observatory. This is one of the early large telescopes built, iconic 200-inch telescope. And here's the 48-inch telescope. It is with this telescope, something called the Palomar Observatory Sky Survey, POS, was undertaken in the, starting in the late 50s. And it took about 20 years to finish surveying the sky in just two bands. Photographic plates, you actually took large photographic plates and exposed them for an hour, went into the dark room, chemicals, then later you got a picture, and that's why it took such a long time. Here's a picture of the sky at infrared wavelengths made by a survey called 2MASS. It took less than 5 years, 3 bands, exquisite photometry, meaning the fidelity of the data is much better than what we had before. And again, this is more slow at work because the sensor technology had grown so rapidly that you could in fact use electronic sensors to make this picture. Okay, so now let me return back to this accelerating return. So my hypothesis for accelerating returns, which I do think actually exists in technology, is that the fundamental, the reason you get sometimes accelerating returns, even when you don't have exponential growth, is that when two technologies are roughly comparable, then suddenly new things open up, okay? And you see this sort of effect in, for example, in the history of Earth, when there's a big climate change, suddenly there's a huge growth of species because the two things inspired, the weather, the motion of the continents. So in the same way, I would say that even in the absence of particularly exponential growth that's driving this, if you have two technologies that you can combine, then you'll get a fantastic growth. So I'm going to justify this particular statement in the next few slides. So here's the reason I want to work in these areas. Now, I don't have time to work in all these areas. I like to switch every 5 years, keeps my brain fresh. But also, the one reason I like to switch is it's always good to be there before the rest of the people have gotten to it. So the first, I give you for one advice already to the young people. The second one is very simple. Don't work in areas where other people are working. Okay, so if you go to a place and everyone is quantizing gravity, avoid it. Okay, unless you think you're very bright. Now, statistically, that's very unlikely. Again, remember that. Okay, so if you're young, you should always figure out a new angle because that's the only thing in your favor. Old angles, you have nothing in your favor. Okay, so that's why I like to switch, and I always try to figure out where is it? Where is all the action going to be a few years from now? Better still, can I make that action happen? Okay, so dark matter and dark energy. I think this will progress because this is all related to what I call as massive multiplexing, the ability to make very large number of spectrographs. These days, making spectrographs of 100 is considered a challenge, but the technology is now available to make them in the thousands, actually. So that will be a growth area. I'm not going to be working in that because I think the whole thing is very boring. A search and characterization of extrasolar planets, well, that's very interesting. I think this is one of the most interesting things. This will really require many technologies. So this is a very fertile field. If you get a chance, you should work in that. Synoptic imaging at radiant optical wavelengths. Just imagine, what if I could take an image of the whole sky every second? I'd make tremendous. I would now make a movie of the sky. I won't be taking static images. I'll be looking at the sky changing. I'll find asteroids, find explosions. Okay, well, that's all easy for me to say. Do I have the ability to look at 40,000 square degrees with 1 arcsecond pixels with a reasonable magnitude? Well, not today, not yet. This is a very challenging job. But can I do for a % of the sky? Yes. So I think this is very, very interesting. And the same thing is happening in radio because both of these are driven by Moore's law. In optical, it's the sensor technology, the CCD. The way to make CCDs is getting better and better, that you can buy the CCDs cheaper and cheaper. Radio, it's quite simple. The fact all of you have cell phones, it has all sorts of little filters and low-speed computing that, in fact, make a lot of the radio synoptic imaging possible. So you want to be in that because you're not spending money doing that technology, and yet you can apply that. new bands like the submillimeter, this is great because I think this is a case of an accelerated return. I can't go in detail now, but the submillimeter band, it's been very difficult to make very low noise detectors. And it's been difficult, as usual, to make them in abundance. But it turns out there have been two separate trends that we can now make both low noise as well as a reasonable number of pixels. That's why you'll see this will be one of the very easy areas to be working in. Strong gravity. I don't mean, again, theoretical gravity at all. It seems to me right now understanding gravity is reasonable. The thing is we want to verify what happens. Really, these Einstein's equations hold true when V over C is not something like 10 to the minus 3, but 10 to the minus 1, okay, in that limit. And it's possible because we'll soon have advanced LIGO, Virgo, and LCGT that would in fact allow us to see coalescing neutron stars. Okay, so I'll just pick a few of these topics that I thought through so that it'll be more real. So don't misunderstand that the talk from now on is, I think, what I thought rather than a very general thing. Okay, so let me give gamma ray bursts as an example of technological convergence. Okay, so gamma ray bursts were discovered in the 60s, late 60s, after the signing of the Outer Space Treaty. Up until about 64, you could build an atomic bomb and you could explore it on the surface, get nice mushroom clouds, great photo opportunities. But with this treaty, above ground explosions were prohibited. And all the explosions then had to be done underground. And in order to make sure that these were not done in space instead, both US and USSR launched satellites whose main job was to look at the hard X-ray emission that inevitably accompanies a nuclear explosion. And this is an artist's conception of the Vela satellite, which is a system deployed by the US. Sure enough, they did find very short bursts of hard X-rays, sometimes called gamma rays. And after some amount of just using simple triangulation, the constellation of satellites, it was established that these are not of terrestrial origin. Gamma bursts, they roughly happen once a day, maybe a few times a day, somewhere in the sky rather isotropically. And if you could convert energy to optical, they'd be actually quite blinding. They'd be brighter than the brightest star that you see in the optical sky. So the origin of these mysterious bursts, which were isotropic, very, very bright, really fascinated astronomers for a long time. This is a debate that was held in the same style as the original distance debate, and this was like 1995. So that's about 30 years later, approximately 3 decades after the discovery of gamma ray bursts. Astronomers didn't know whether they were isotropic and nearby or isotropic because they're so far away and the universe is roughly isotropic. So you could go to this debate. It was a room like this. I actually went to this debate, and there are 3 sections, and you could sit in each of the sections. You could wear a button which says gamma rays are galactic or they're cosmological. Or if you're undecided, you could sit in another row which there are others. And I'm always very sharp about such things. I said, I really don't care where they are, but the collection of 3 buttons, which are somewhat historical, I collected all 3, and I'm always willing to negotiate with you guys, and if you want. This is a rare set. It's great value. Okay. Well, it turns out, like many times in many sciences, the answer is never it is this or that. It turns out actually mostly they're cosmological. Actually, it might be that numerically, if you just normalize it by the volume density, there are some which are galactic, and there are some which are other. There are these repeaters which, in fact, look like gamma ray bursts and confused with gamma ray bursts, and they're nearby. You can see to sort of the local group of galaxies. Okay, well, that's going a bit ahead. So in 97 or so, the Italian-Dutch satellite Bepo-Sax was launched. And it carried in, if you look at it, perfectly ordinary X-ray and gamma ray detectors. Nothing special about those things at all. Okay. However, I will giving you a bit of the punchline. However, this satellite made huge progress in less than a year following of what that is, a burst goes off, and if you go and then look there again, you energy radiation. Astronomers are able to demonstrate that gamma ray bursts are of extragalactic origin. That came about a burst called 970508, and that means it happened in 1997, May 8th. I'm terrible with dates. I never remember my own birthday. I mean, it's just a phase in the solar orbit. Who cares, really? But actually, I do remember my wife's birthday because this is this to be her birthday. So I told her, I'll never forget your birthday from now on, because it is with this burst, astronomers are able to show they're extragalactic. Okay, then what is interesting then is that some of the bursts you could then go back and show, you get the redshift, they turn to be quite high. And in one case, if you just say, what is the flux, what's the distance, and assume the time scale sets the physical scale, you compute the density, energy density, and it would be, here's this famous picture, I forget from which book it is, which shows the energy density in various units as a function since the universe began to now. And gamma ray bursts were, in fact, up here in almost imitating conditions in the early universe. And I have a colleague who's very, very creative, and he said we should call it as Big Bang 2. I liked it. It sounded like a completely good way to analyze your work, but of course completely false, because the Big Bang is an explosion that happens at every point, and this is in that sense an explosion only at one point. Nonetheless, my fears were justified because, in fact, I had this poor young student from Indore a letter to me asking if there are things within this Big Bang too, universes and so on. Okay. So anyway, the part I liked most was this happened around the time of the Indian nuclear test, and so I love this. Indian detects Big Bang 2, and of course this is where I was born, and as a result, I got a nice homecoming trip. Where I was born, the villagers wrote me a letter. I had a great parade, and it was fantastic. So this paper was well worth it. Okay, but the one I like the most is here is a German newspaper. It's Bo Derek, and I was suitably overexposed because she's not wearing any clothes. And this is the see stuff because it's got Bo Derek, it's got murder of the Pope, and somewhere here it actually reports our gamma ray burst work and says thus is extreme phenomena Shrinivas Kulkarni. We are mainstream. I mean, we are absolutely mainstream at this point. That's when you know you're doing great science, right? Okay. So what are the ideas? Well, the ideas are the gamma ray bursts we now believe are the birth cries of rapidly spinning black holes. And there are two ideas. And one is that you have two neutron stars. They're close enough. They've got gravitational wave radiation. At some point, they'll coalesce. In fact, this is the beautiful work done by Joe Taylor, who showed that in the 1913 plus 16 binary system, in fact, the orbit is shrinking, just with entirely in accord with the expectations of general relativity, which means they will at some point make contact. And then the idea is two neutron stars merge, you get a black hole. You feed a bit of matter, things come out, jets, what have you. The other one is you start with a massive star, and so it's a it's exactly the opposite because this involves two dead stars. This is a very young star, and then it does the whole thing. It has nuclear fusion in the center. You reach iron, at which point it's endothermic, the reaction, and then it collapses at that point. And if this star has any amount of small amount of rotation, remember there's a huge amount of angular momentum because the lever arm of the star is very large. So when it collapses, the black hole would naturally be one spinning very large, unless, of course, the angular momentum has been transported away. So that's another idea, and that's called as the collapse idea. And we now believe that, in fact, both of these channels are actually active. This channel gives rise to what are called a short, hard gamma ray bursts with a duration of less than a second, and the long ones we believe come from this particular channel. Okay, so what led to this breakthrough? Why did it take 30 years to uncover this obviously blinding phenomenon? This is not a subtle thing. Gamma ray bursts are not subtle. You can build a small sodium iodide crystal only this much in size and detect them. The gamma ray sky is dark, few photons, you're ready. Well, the X-ray and gamma ray detectors on Bepo sacks, they've been around for decades. There's nothing special about them, okay? But I think the reason this happened is that Bepo sacks happened at the right time. We had large format detectors, so when Bepo sacks could, both it could slew, it could communicate because of large internet bandwidth. Not only they could detect it, but once they found something, they could put it on the web. People could read the stuff. So rapid dissemination of information was possible thanks to the internet at this point, and data reduction. You could take CCD images, reduce it in a minute later. You know if you have a new source or you don't have one, and you can communicate. So I would say this is an excellent example where there is no great technology here. All this technology has been around. We all were using internet before, a year before that. In fact, many years before that. So these CCD detectors were not particularly large, but of course much larger than the previous era. But the combination of all these things is why in 1 year you went from the mystery of gamma ray bursts to actually sorting, to actually having tremendously great progress. Okay, so let me move on to the second topic, which is synoptic optical imaging. So when I say synoptic, the idea here is basically large field optical imaging. Can I make images of large pieces of sky? And there are obvious reasons why I want to do this. I want to find, let's say, asteroids. They move in the sky. So you take a picture, you come back 10 minutes later or an hour later, take a picture, and you find it moved, and that's how you find asteroids. Or you come back the next day and you find explosions, supernovae. And the larger the field of view you have, the more things you find. Okay, so here's a way to understand what these explosions might be. On one axis, we have the time of explosions. I'm here focusing on basically non-relativistic explosions. And on the other axis is an astronomer's unit, but for right now, you can just regard this as peak luminosity, where the more negative the number, the brighter it is. And this is not log scale. For a long time, astronomers know something called classical novae. They've existed. They were one of the earliest explosive phenomena found by astronomers. And the so-called 1A supernovae, which are fashionable now because they were the supernovae which gave the first clue of dark energy. And then we have luminous blue variables, and then an emerging class of something called luminous red novae. Now, most of these other stuff here, they're ideas. They're ideas. Okay, that's what I told you. Ideas are cheap because when you put up a figure like this, it's quite easy. Okay, this will take 5 minutes. It'll take a few days to figure out where these things might lie. So here, for example, is a fallback supernova. Okay, so if you think there's a large star, it becomes a black hole. So the question I ask is, what's it going to look like? Well, this is a little bit more sensitive. This is not as easy, but you can argue, in fact, this will be very dim. Because when the strong shock wave goes off, if most of the nickel is advected into the black hole, then you don't expect to see it as a bright thing. So we don't know. There's a huge amount of uncertainty in this. Understanding this would, in fact, tell you something very interesting about the formation of black holes. So most of these boxes are yet to be discovered. They're plausible ideas. Many of them will come up in white papers. The key thing in this business is not plausible ideas, is to go and make that discovery and write that first paper which says, I found it. Okay, so how do you do that? The only way I know is you go observe. Okay, and you build ever more powerful instruments so that even if you're not bright, you can make the discovery. That's how instruments should be built. Okay, so a few years ago, I started a project with a specific focus of trying to look at the dynamic sky, that is, the sky as it changes. So we image with this 48-inch. This is the old 48-inch I started the story with, but now we have a CCD. Instead of photographic plates, we have CCDs. It's about this in size. It's much more sensitive, 100 times more sensitive than photographic plate, so you can really observe about a few thousand square degrees per night. And then we analyze the data in real time, and then if there are any transients found, we observe that with the 60-inch telescope. It's all robotic. There's no person sitting there. And then we'll know what the color is, what likely this explosion event is. It looks very interesting. Then we observe with a spectrograph from the 200-inch. And to me, this is a case of an accelerating return, because each of these have been done before. Large format detectors have been used, photometry has been, spectroscopy. But to do this all in one night, that is new, and it enables new discoveries. You can't do this sort of stuff in a single, by yourself. So this is a group of people put around the world. It has from Berkeley, IPAC, Lawrence Berkeley Lab, Columbia, Oxford, LCOGT in Santa Barbara, Weizmann Institute in Israel. And you can see most of those people are young. So I told them, look, I have no money. You come and work for me. I'll make you famous. And they're all getting lots of papers. We are now writing a paper about every 2 weeks because it's so productive. You just wake up in the morning and say, yeah, how many discoveries have you made? What's interesting? Yeah, why don't we write a paper? And we can do that because this whole triad is now discovering one transient per 20 minutes. It's amazing. Next morning, you go, you have something of the order of 30 new transients. Mostly supernovae, mostly 1A, mostly boring, but once in a while something very interesting happens, and one strong variable per 10 minutes. And we are just barely scratching the surface. Okay, so one of the key findings we have is finding the brightest supernovae. These supernovae, we now are finding about these incredibly luminous supernovae, which we believe, in fact, come from the deaths of very, very massive stars, perhaps 150 solar mass stars. These sorts of supernovae will tell us a lot about the very young universe, because the same sort of supernovae are supposed to occur in these galaxies. So I'll be talking about this, in fact, a bit tomorrow, the whole project. Okay, so moving on, synoptic imaging at radio wavelengths. So the optical stuff is all being driven by the huge progress that's being done in optical sensors. And the radio is basically being driven by the kinds of stuff that we all are using, and satellite TV, cell phones, and what have you. So here's an old telescope, the Parkes. It's one of the earliest telescopes, 64-meter Parkes radio telescope. And you may be surprised that for a long, long time, these radio telescopes are what you call a single pixel detector. So the rays come in, they get focused, and it goes to one spot. So it's as though you have only one detector on your eye and you're going around. So if a radio telescope has to make a movie, make an image of the sky, then it has to raster it. There's, observe, observe, observe. So it rasters, and then after a while, you have that. Very, very slow. Technology works. So here's something that, the reason that it was done that way is not because radio astronomers were stupid or something. It's very expensive to make these detectors. But in the mid-90s, it had become inexpensive enough to make these detectors. And this is called the multi-beam, and it has 13 beams, so 13 pixels instead of 1. And with this small modification, the Parkes group found as many pulsars as the rest of the world had done integrated to that point in a few years. Okay? And that's when you get exponential growth. They found amazing sorts of pulsars. Double pulsar system, for example, is a great find. Things in globular clusters, all sorts of wonderful things. And in fact, some of the best tests for experimental GR are being done by the double pulsar found with this system. The system also found something called a very sharp burst. There are some doubts whether this 5 millisecond burst is real. If real, it would be amazing. It would be, I'm not sure this is real, but if for a while it was considered real, if real, it would be perhaps, one of these weirdo things which may even turn out to be right. One of these superconducting, colliding, whatever thing is that sometimes the string theorists talk about. But we don't know what, but this is not very real. But the point here is that this instrument now has the ability to go and look for some amazing new things, and already has demonstrated very well. Here's a Dutch LOFAR project. And this is the opposite frequency. This is a frequency range at a meter wavelengths, just like GMRT does. And this is an old band, but the computational power that's now available and the ability to do both hybrid analog and digital work on actually have a small chip, which is basically radio on a chip, helps astronomers in the same way. So with this, the Dutch are actually exploring the 100 megahertz sky quite well. And who knows? They may find some new phenomena. They may not, but they certainly will be studying the young universe. Here's an entirely different approach with the Allen Telescope Array. And this actually works on the idea that you make smaller dishes. And it turns out if you make smaller dishes, in order to get the same area, you need lots of those dishes. The electronics cost goes up because each of these has electronics. You have to multiply the voltage here with the voltage there, so that it goes as n squared. But electronics cost is falling. Your PC is getting cheaper every day or every other year, which means that what was considered impossible even 10 years ago is possible today. And that alone gives you an amazing mapping speed. So the speed of this array, even though it is rather small compared to the very large array, which is an expensive state-of-art $500 million project, is comparable at this point. Okay, so what could you do once you have these sorts of high-speed arrays with radio? I think one of the most exciting things is if you can combine these high-speed machines in radio and optical with advanced LIGO. So as all of you know, the LIGO project, to me, is astonishing that they actually were able to reach the design sensitivity they claimed in their first phase. So they're now on to their second phase, which would now make it possible for this project to actually see or detect the radiation from coalescing neutron stars out to a reasonable distance of about 100 or so megaparsecs. And if we at all we understand this business, this should be detectable, they should be reasonably frequent. And I think this will open up a whole new chapter. If I was a young all over again, I'd be working in this sort of stuff because our ideas are there, they look very reasonable, but we'll actually be able to make measurements. There's one problem with LIGO, and in general gravitational wave astronomy, is that the localization by these machines is very poor. All said and done, LIGO is just basically a 3-element interferometer working at 100 hertz. It's not, which is the gravitational frequency of when it's most sensitive to the coalescence radiation. So the antenna pattern of localization will be very, very poor, okay? And so we won't know. We'll know there's a gravitational burst or a chirp signal coming, but we don't know where it is from, okay? Even if they're localized to something like 10 square degrees, which in this game is really great, it doesn't mean anything. 10 square degrees has the whole universe in it. You have to localize to much smaller than that to actually do a better job. And therefore, you'll need these high-speed machines. So this is, again, what I call as a convergence technology, because there has been no exponential growth in the LIGO's business. This has been a very expensive project where the growth in sensitivity has been very slow. But if you can combine the detection of a strong burst of gravitational waves and localize that using electromagnetic high-speed machines, well, then I think you've done something really great. So we looked into this problem. I looked into this quite hard. Here's typically an antenna pattern from combining LIGO and Virgo. You can see this in degrees, so it's not very good. This is more or less, in my opinion, the whole sky. But if you have these high-speed machines ready, so we can really then undertake rapid observations the same night, we believe it's actually possible to localize the LIGO events starting perhaps even as early as 2014 or 2015. There's a lot of work we need to do, but I consider this to be one of the more exciting things that I think will happen. Okay. So the last one I want to talk is the lush sub-millimeter frontier, and I call it lush because, as I told you, the art of being, it's like in life, you never want to, or in my opinion, you should always work on easy things. Easier and where it is the gains are great is what you should do. There's no value in working on hard things and feeling very good about it because you won't feel good about it 10 years later. This is the field which is where, if I was young, even younger, I'd be working, because it's going to be absolutely easy. The sensitivity gains will be so large that you just take a telescope, point anywhere, you can write a paper. And that's exactly where I'd like to be always. Okay, that's why I have this very nice beach picture, because this subject reminds me of going to the beach. Because right now we write a paper every 3 weeks. Well, it's a bit work. This one I can write every day. Okay, why do I think so highly of this field? So here's the submillimeter, which is roughly the 100 gigahertz to a terahertz. So let's say about 100 gigahertz to about 500 gigahertz. This is one of the early submillimeter things. So let's look at something called the NEP, which is roughly the quality of this detector. The smaller this number, the more sensitive this detector is. And 10 to the minus 14 watt. Okay, let's remember that. That's the first astronomical submillimeter or millimeter wave telescope, and Frank Lowe was one of the pioneers who passed away a couple of years ago. This game has been limited by the kind of detectors. So Frank Lowe is an applied physicist who realized the value of germanium bolometers for this project for astronomy, and he essentially became an astronomer at this point. Okay, the subject basically then, another physicist, Robert Layton, developed very clever ideas of making these very precise dishes that were inexpensive. You really have to making these dishes with RMS of less than 100 microns, preferably 30 microns, and cheap is not easy. But Layton was an amazing guy. He developed this technology. Okay, so what can you do? So I've sort of given you a rough idea. There's this field where it has been hard to make the detectors, hard to make the telescopes, because it requires great precision, much fine detectors. But the subject became really interesting if you plot in a sense, the spectrum of the universe. If you go and look at, I just look at the telescope, add up all the points, I get a spectrum here, spectrum there, all over the thing. And if I plot the spectrum as a function of wavelength of the entire universe, this is what I've done. Okay? So this is the great spectrum of the universe, and this is, of course, the famous cosmic background radiation, the 3 Kelvin radiation. And then this is the optical background. This is simply the sum of all the optical galaxies. Okay? We knew this, we knew this. What is interesting is, it was only about 20 years ago or less, we realized there's this amount of radiation here, which is actually comparable to the amount of radiation in the optical band, and peaking in the submillimeter. Okay, so there's this whole universe out there, about half the energy, which we don't study. So that immediately makes it very, very interesting to study. Okay, so with great effort, this is a scuba detector on JCMT, James Clerk Maxwell Telescope in Hawaii. This was built by UK. The astronomers had to practically bankrupt the exchequer of United Kingdom to just make this detector, because it's concentrated is one type of galaxy, but there's an equal amount of star formation going on in the submillimeter galaxies. Okay, so that's sort of, so it looks very interesting. There's obviously some gain to be made, but here's where this field is. If you plot the exponential decrease of this NEP, d log NEP by dt, okay, that's great. It's changing every 2 years. But it's not Moore's law. It's just this sort of a law where we are understanding better of this solid state physics here. And it went all the way from 10 to the minus 14, which is Frank Lowe's first measurement, to of the order of 10 to the minus 19 now. And you can then look at a genuine Moore's law, which is the number of pixels as a function of time, and you can see, in fact, that's also increasing. Okay, these are real points here. Scuba 2 is actually, I think, operational, and this is something in the future. If you can combine these two, this is where there'll be a huge amount of action. And therefore, there's a project called CCAT, which is a 25-meter submillimeter telescope. But the way to really look at this project is the other way. Now, normally astronomers think, or you think, you build a telescope, then you say, what do? I put a detector. In this case, it's the opposite. First, you build the detector. So first, you build a large submillimeter camera with a spectrometer. Then you say, what do I need? I need a telescope. Okay, then you get the telescope, because that's what this project is. That's where this field is. Anyway, so I hope I have not a talk like this is always difficult to hit the right tone, but I hope I've given you a rough sense that, with technology, whenever there's been huge growths, any astronomer who happens to be there at the right time, right place, you can make discoveries. I know this very, very well because I've been there at the right time, right place so many times that I just want to, in fact, always be at the right time, right place, because then you don't have to be smart. Okay, so now, since most of you are not smart, you should be listening to me. Okay, now I know during this conference you'll be listening, you'll get, you'll hear a lot about vacuums, the string theory, black holes, antimatter. It's great, it's fantastic stuff because you go to a cocktail party, you can always throw a word, event horizon, thing you heard recently, and you can always impress people. Okay, that's one of the reasons, of course, one attends such conferences. Me, at this point, you got an idea. I'm one of these absolutely practical guys, so I want to give you something much more useful than these sorts of horizons and symmetries and so on. I want to make money for you. Okay, so next time you go to Australia, here's how you can make some money. Now, Australians are very nice guys. They're a bit naive, I think, in general. So you should catch hold of a local person and say, hey, show me a $50 bill. I'm going to show you something very, very interesting. The person will produce one. Then you say, well, this is the Parkes telescope, and it's finding a lot of pulsars. Here's a pulsar signal. Talk a little bit about the multi-beams, a little bit about a few things to remember about my talk, throw in a few words. And this is where you have to do a bit of work. You do a good sales pitch, person is happy, pocket the $50. That's it. Okay. That's it.
Thank you very much, Shrinivas. Like Abhay, I was wondering what Chandra would have done now. Should I characterize, in fact, I tried to characterize the talks in my own notes. Should I characterize it as extraordinarily informative, provocative, entertaining, sexy, what not? But finally, I decided it was extraordinarily informative. I thank you very much for the nice talk which you have given. I enjoyed it myself, even though I do try to quantize gravity once in a while. Unfortunate. Okay, now we'll wait for the questions.
Yeah, so I have one thing to say in that, and I'm not planning to mention that. So actually, I did meet Chandrasekhar a long time ago. The University of Chicago asked me to give a colloquium. I said, yeah, I will, but I'd like to meet Professor Chandrasekhar. So I was granted an audience. And that's a time, a few years after I had found the first millisecond pulsar. There's a lot of interest in very precision timing and of this sort. So I was speculating with him that if you had a double pulsar, you could really do accurate tests of GR. And his reply was, it said, GR is so beautiful, you don't need tests. And I said, Professor Chandrasekhar, you're a great person, but I completely disagree with you. It is only when you find the deviation from GR, you'll have found something even deeper than GR. But anyway, I still stick with. For
that you have to do quantizing gravity. Deviation from.
Okay, anyway, I'm happy to take questions.
Sure.
You mentioned about exoplanetary research as one of the important areas. I keep reading about them. It's very fascinating. Are there efforts in India? It's a general question in this direction, because I have not heard Indian astronomers or astrophysicists.
Yeah, this is, I hate to say, but exoplanets it's a very, you have to be very rich to play the game, in my opinion. It is not a game which can be played, no. I mean, there's a lot of action in optical, in perhaps a sub-millimeter, in the infrared, astrometry, but all that stuff is quite expensive. There is one program, having said that, one program at GMRT that I know a group of people are doing, which is, in fact, to sort of look for hot Jupiters. That is, you have like a Jupiter Io phenomena, which could be an accident. I mean, you know, Io has volcanoes, and it's almost a nice conductor. There's strong magnetic field. So the fact you have this decametric burst from Jupiter, which are amongst the strongest radio source in our solar system, and the Earth itself is a very strong radio source. The AKR, the auroral kilometric radiation, we are the strongest kilometric radiation in the solar system. But if you just take the solar system, even put it in the nearest star, Alpha Centauri, our most powerful radio telescopes can't find them. But if you shrink the solar system, make some approximations, maybe you can scale up the Jupiter Io phenomena for so-called hot Jupiters. And there is a project like that at GMRT. If they find it will be great, it's a more chancy thing because it's less assured. But as far as I know, that's sort of the only leading edge extrasolar planet work I know being done in India.
There's a question about the Perlmutter experiment more than 10 years ago, where you had this supernovae tracked by looking at the CC pictures for a large area of sky, and then specifically pointing a telescope to something interesting. Can you control experiments, satellite-based experiments, the same way as you can do with the base experiments? Is it possible to control from the Earth specific instruments and these satellites to do the jobs when you know there's something interesting to do right now?
Okay, which way do you want to go, from Earth to space or space to Earth?
Earth to space.
Oh, that's done reasonably routinely. There's a, you know, it's certainly that was one of the big strengths of some new mission or a recent mission called SWIFT. And as the name says, it is SWIFT. You can send a command and it autonomously slews. So we, in fact, can be many times with the observations we do with PTF, we, in fact, just simply fill up a little email request. And sometimes in the same orbit, it gets observed depending on the load they have.
You said otherwise?
Otherwise, pretty straightforward. It's been, yeah. Gamma ray bursts, they come to my cell phone, anyone's cell phone. There's a little bit of delay as it goes through TDRIS or a little bit of internet latency, but that's pretty straightforward now.
So, Shri, you talked a lot about how new technology has really allowed detector power to exponentially grow. Has there been anything similar on the telescope front, or is there something we can look forward to, an exponential somewhere?
No, well, that's a good question. The cost, for example, of telescopes now, optical telescopes, is about $1 million per square meter, okay? It's not changed a lot. What has changed, so in the range of 1 to 5 meters, it's roughly d square with that coefficient of $1 million per square meter. What has changed is with the segmented telescope, in the past, if you just didn't segment, it wouldn't continue as d square. It would have steepened up to d cubed, d to the 2.7. The segmented telescopes have allowed you to break that beyond 5 meters. So one of the interesting ideas here really, I mean, that I think is worth really taking a hard look at, in my opinion, is can you segment small telescopes? The big telescope is segmented because of purely material reasons. It's very hard to make a monolith more than 8 meters. But if you could segment, let's say, a 2-meter telescope, then I can use very thin glass and fine actuators. Can I break this $1 million per square meter? In fact, this is something I've been thinking a lot with Roger Angel, because if you can break this, it'll be a whole new type of astronomy that can be done. But you know, as you know, the reason these other fields are more easy to do things like high bandwidth processing, Wi-Fi stuff, or CCD technology is because we don't pay for that. Someone else is paying. Whereas this is peculiar only to astronomers. So the investment, the capital investment. So these are sort of things I think countries which have not been in astronomy, like China, India, should be looking at, because if they can get on that, then you know, you're not trying to do the same old thing.
just a comment and a question. I mean, I had a lot of discussions with Chandra along the lines that you said, and I think it is, his point of view was more that something like tests of general relativity within solar system, or even double pulsar, are going to confirm general relativity. That was his point of view. I mean, I agree that, science is experimental and one has to test this. So it's not so much that he didn't want to go beyond general relativity, but he wanted something even more dramatic than something like a double pulsar. So that is my understanding of his point of view. Okay, my question is the following, that you had these very nice pictures about the Virgo and LIGO things. So they were just computer simulations of something, is
Right.
it?
Yeah.
Right. And then what the idea is that supposing I had this blob in the square radians, then you're going to have optical follow-ups quickly.
Yeah.
Is that, so where are we now? And you said that by 1214 we might
Okay.
be able to get there.
The
So
reason,
how does it?
yeah, so I can tell you it's a bit more involved than. So the reason, this is a very large blob. I mean, this is, and this is a really realistic, I forget, one of the LIGO teams actually did, these are contours of equal probability and that sort of stuff. This is a very large thing. But the way you can simplify this is that if you have a third dimension, which is, roughly, at this point you do believe GR and say, I know that this event cannot come beyond, let's say, with the sensitivity I have beyond 100 megaparsecs or 150. So all you have to do is take this blob, okay, and then find which are the galaxies in this blob which, in fact, are in the redshift range that is appropriate. Okay, so you have to image the whole thing, but you don't have to study every galaxy. And the decrease you actually get is simply the ratio of the nearby galaxies to sort of the rest of the universe. And that reduction is a factor of 100, it turns out, for advanced LIGO. Now, as the LIGO instruments get more sensitive, it becomes worse, because then at some point, it will go into a very large distance. Half a gigaparsec is, but I'm not worried. I mean, we are looking at, I think we've got to make a discovery before we plan these things. So at that point, then the question is within the same night, because the idea here is that you have this coalescence, maybe there's a small amount of debris left, and there is, even if it is something like 10 to the minus 2 solar masses, the photon diffusion timescale is long enough that it lasts for a few hours. So in that few hours, you should be able to rapidly study each of these galaxies.
But what is the estimated number of galaxies if you look at this 100 megaparsecs and this?
Yeah, I
this
hate to
blob?
say, but I actually, my student, I do have a white paper on this. So I'll have to look it up.
Well, he did say he's not going to do cheap things.
How about some of the younger people? Well, first of all, there's mass segregation. This is a thing that happens in astronomy. In a globular cluster, the more massive stars, which are also the older stars, neutron star, white dwarfs, they come to the center, like closer here, and then the younger star,
No, there is one reason for that.
Anyway, so maybe one question from the backbenchers before we call it quits.
Sir, is there any scope for optical interferometry in the current research telescopes?
Optical interferometry it has its run. It's a hard game. It's a hard game. I think it's more limited, in my opinion, at this point.
Even with the electronics that we are
No, that's the
experiencing?
problem. This is not an electronic problem. If you tell me how I can take one photon and split it many ways, then we do interferometry. The problem in optical interferometry is that you can't amplify photons. So the only way out of this business is the brute force way. So none of these new technologies help optical interferometry.
What is the scope for that in the future?
Okay, the question is, what is the future of neutrino astronomy? Well, it's a broad field, but there are roughly two kinds one can think of. One is the low-energy neutrinos, the sort you would find with the supernova, okay, like Kamiokande found with 87A. And then the other one is very high-energy neutrinos. Okay, we already know that ultra-high-energy cosmic rays up to energies of 10 to the 21 eV exist, and so it's not unreasonable to think of extremely high-energy neutrinos. So there are these projects already in progress for both of these things. The galaxies, we are overdue for a supernova, so astronomers are anxious to have one go off in our own galaxies, and I think it'll be quite fun, but the rates are very small, so